students, and welcome to HSC Chemistry. This is Chemical Monitoring and Management number 20, and today I'm going to just quickly look at the relationship between CFCs and ozone and some of the ways that we've tried to address this concern. So you'd be aware now that the section of the syllabus that involves ozone was basically prompted by some significant issues associated with holes in the ozone layer, particularly around the poles. And so a lot of work, a lot of agreements were being put in place in order to try and address these problems. And the problems stemmed from the use of CFCs. These were causing destruction of ozone once they reached the stratosphere. And the problem was the cyclic nature of the chlorine-free radical, because it was able to destroy thousands of ozone molecules just by binding, taking away the oxygen from the ozone molecules and then re-releasing it, and then being available to do that again. So it's effectively acting as a catalyst, facilitating a reaction, a breakdown, and then remaining afterwards to go and do the same thing again. The problem was a decrease in stratospheric ozone, and ozone in the troposphere is a problem because it's a pollutant, but in the stratosphere it's very, very important because it provides that barrier for the Earth against certain types of ultraviolet radiation, particularly B and C. And so concentrations, particularly at the poles, were decreasing, and this was first detected in the 1970s and 80s. They were described as marked decreases in the concentration of ozone, particularly around the north and the south poles, and because of the cycle of ozone formation and decomposition and the relationship with the amount of ultraviolet radiation that was able to penetrate to the Earth, a decrease in ozone concentration was very, very serious because it was increasing the amount of radiation and being linked to the increased incidence of things like melanomas. Specifically, some of the problems with increased ultraviolet radiation includes sunburns and skin cancers, melanomas, which is one of the problems that we have in Australia, or at least we had to a much higher extent. Eye cataracts, a decrease in the immune response, also some plant damage to phytoplankton in the seas as well as land, and polymer decomposition as well. So the only way we were going to be able to deal with this was to stop this ozone destruction and get rid of the CFCs that were going into the upper atmosphere. This is a big slide of stuff, but it's probably important to just get a little bit of a feel for what's happened. When you look through this, you can see the Vienna Convention, the Montreal Protocol, the London Agreement, the Copenhagen Agreement, and subsequent additional signatories that have been added over the years in order to try and combat this problem of ozone depletion and a use of CFCs. So you can see this whole process began in 1985. In the Montreal Protocol in 1987, it was about freezing production and reducing production by 50% by the year 2000. A later London Agreement identified the elimination of CFCs and halons, and we'll have a look at those later on, and also carbon tetrachloride, and giving a little bit of a generous time frame for developing nations who may not have been able to turn them over as quickly. 1,1,1-trichloroethane was on the hit list, as well as the HCFCs by 2040 at least, but preferably 2020. We'll have a look at some of the HCFCs a little later in this video. Copenhagen Agreement was another agreement a couple of years later. You can see really targeted use of CFCs to try and not just reduce production, but actually to eliminate them. The problem was so big that you can see some changes of goals to reduce production, which then later changed the goals to just knock them out altogether. And the fact that we're now in 2016 means we can look back on these agreements and see what's actually happened, and what we notice is that they've been very effective in reducing the problems of ozone depletion. So I guess the replacements, firstly the halons were developed for use in putting out fires in very large computer systems when they were in rooms and also on aeroplanes. They contain at least one bromo and fluoro group, but they may also have chlorine atoms that don't have hydrogen atoms. But this was not a good solution because similar things were happening, just not quite at the same rate. The HCFCs, which were there, one of the things that we were looking at as a potential replacement as well, hydrogen, chlorine, and fluorine. The problem that we have is the carbon-chlorine bond, and that's the one that really causes those chlorine free radicals, which are the ones that damage the ozone molecules. And so this one again was still not a great solution. The hydrofluorocarbons were then used as well, and they were proving to be better with no critically removing those carbon-chlorine bonds. Very, very important in trying to make sure that there is no possibility for those chlorine radicals to be released. So these are the ones that were widely used as replacements of CFCs. A lot of these carbon-hydrogen bonds present in these molecules, so there's a little bit of decomposition in the troposphere, but no issues with chlorine-free radicals in the stratosphere. So this reduced the ozone-destroying capacity down, so it got the ticks. It was good. The only disadvantage was it's more expensive and less efficient. So we're still looking, we're still trying to find replacements. And hydrocarbons have also been selected as replacements too. They have replaced CFCs as propellant in spray cans, very much more common now for particularly deodorants and things like that. And they're the ones that have taken on the jobs that used to be done by the CFCs. So just a quick overview. Thanks for watching.